Hello, everyone. So today we're going to be getting into one of the real hearts of uh, modern chemical engineering, and this is the idea of mass balances. So you're going to find a lot of very familiar principles that we've addressed in other chemistry classes, except for done in a very different perspective. So the major idea with performing mass balances is trying to figure out roughly where chemicals are going to be located in a industrial process. But it's worth noting that this is the same exact principles that form the foundations of a lot of uh, descriptions uh, of biology, both on an organismal level and also on a ecological system. Because a lot of what you're doing in all of these fields, whether it's in an industrial plant or an organism, is watching what's coming in, what's going out, and what form the chemicals are going to be in along the way. So, before we get into the heart of mass balances, I want to have a quick refresher of some of the things we've learned in the individual unit processes that we're going to be spending some time linking together today. So again, just as a reminder, processes can be either divided into continuous or batch. So this is going to be continuous, is we're going to have a constant flow rate in and a constant flow rate out. And in batch, everything moves as one lump slug. So in order to describe these systems, we need to know how much of the material is entering or leaving the system at any given time for a process, or when we add and remove systems for a batch system. And this is going to be the real art of determining the identity of these quantities is going to be mass balance, because it turns out sometimes all I know is what's coming in, and I need to figure out what's coming out. So what we can do is use some of the tricks of mass balance to help save the day. However, one of the other things we have to watch out for is that these processes, whether they're continuous or batch, can tend to fall into one of two additional categories. The first of which is steady state. So this is similar to what we talked about in physical chemistry, but a little bit different. And this is the idea that all of our variables are going to be time independent. So it doesn't matter when I add or remove system, my, my input and outputs will always be the same. So an example of this might be something like a distillation column. Once I give it enough time to kind of warm up and start, as long as I'm feeding in material, the products will tend to the product streams won't tend to change that much. However, if it isn't steady state, congratulations, it's unsteady. And a lot of variables do tend to change with time. So a good example of this is a batch mixer. So if I throw in a big batch of fats and sodium hydroxide to make soap, it turns out the identity of what's in that barrel will constantly change with time. So it turns out that almost all batch processes, unless you give them a lot of time, tend to fall under the unsteady state. However, continuous processes can either be steady or fluctuate with time. So what we're going to be doing to make things relatively simple is we're either going to assume that we're going to be in the steady state, or if I'm dealing with a batch process, I'm going to assume a long period of time so that my product stream is essentially stable and the reactions have gone to completion. So with that said, let's get into the actual art of mass balances. So mass balance is based on a fairly simple idea, and this is more or less the idea that if I have, say, a reaction, the input of, say, chemical A plus the generation of chemical A minus the output of chemical A, so how much of A did I put in, how much of it left the system, how much of A did I make, how much of A did I consume. When we essentially cancel these out together, everything else should end up adding to accumulation. However, we're dealing with simple systems. So we're going to assume that accumulation is 0. So that input and generation are going to be perfectly balanced with output and consumption. However, we're going to try and work with an even simpler case. Let's just assume I'm working with unit operations, and we'll let unit processes lay fallow until next time. So if I'm dealing with a unit operation, so no chemical reactions, this means that generation is going to be 0. I'm not generating any product, nor am I consuming any reactant. So both of these two terms drop out, and input equals output. Now, one of the really gorgeous parts about this is that it turns out that this is going to apply for both my components and to my total inputs and outputs. So really what we've done here is have a kind of rephrasing of conservation of matter. Anything that I add in has to end up exiting the system. So one of the things to be aware of is when I'm actually trying to solve a real problem, in a typical mass balance, I'm going to be given a certain subset of the following chemical information, of the information I need. Uh, Now, the real trick is going to be trying to figure out how to use the information I'm given to find the amount of every chemical input and output. Now, typically, you're not given all of the information. You're not going to be given uh, the the exact amount of every input and output, but you might be given enough information you can solve for the rest. So let's go ahead and take a look at an example process. So let's say I've got a sugarcane processing facility and I'm taking a whole bunch of sugarcane. So this is going to be a nice solution of sugar and water. So this is kind of the end product material. And I'm producing, say, 10,000 kilograms per day of sugar, which is about 38% sugar and 62% water by weight. So I'm going to feed this into a drying unit, and it can be split into water vapor. So this is going to be pure water vapor and a certain more concentrated sugar solution. So I've removed a certain subset of water, and now I'm dealing with a more concentrated sugar slurry. So one of the things is that this will completely encapsulate the system that I'm dealing with. From this, I can figure out the weights of, each of the total mass of the sugar and the water present in each of the streams. However, we're not always so nice. It may end up being something like we know perfectly the weight percent of my input, but not the weight percent of the output. And you'd have to solve for such. So if you run into one of these cases, we have a series of straightforward steps to solve a mass balance. So the first thing we're going to want to do is identify a basis. So this is going to be a quantity of substance. So as in the last case, I already have a basis given to you, and this would be the total mass of sugar solution entering the system. However, turns out you might not know that. We might not know the total mass coming in, so you'd have to artificially choose a basis. So again, this is going to be the absolute number that you're basing the scale of your system on. This won't always be given. If it isn't, choose the one that's the most convenient for you. Now, this next step I can't emphasize enough. A lot of these are very messy word problems. So the first thing you should always do is draw out and label a flowchart. This will really help you quickly identify what you do and don't know. So with that, with a flowchart in hand, you should be able to hopefully identify what the unknowns are that you're solving for. So what pieces of information are missing. Now, when you're identifying the unknowns and labeling your flowchart, this may end up include choosing a formalism. So this is a little bit of what we talked about last time. And this can be the idea of, like in the last problem, you may end up having the total mass of the system, which may be given as a flow, which it was for us, but on a daily basis, with the mass fractions. Alternatively, you may end up have the total moles entering and leaving the system plus the mole fractions. And then finally, you may have the mass and moles of all individual components. As a tendency, chemists tend to be most comfortable with this third option. But from what we covered last time, don't forget, you can always turn options 1 and 2 into 3 if you can. This will probably be the one you're most comfortable with at the moment. Now, with a diagram, a basis, and our unknowns identified, what we can do is try and identify what equations we can use to solve for all of our unknowns. So it's worth noting that these will often take n equation, n unknown systems. So there's going to be usually 3 or 4 equations you're going to need to solve in serial. That said, once you have your equations, the last step is the easiest to say and often one of the hardest to do: solve. Now, one of the things to watch out for is you may have decided at this beginning that you didn't want to use the basis that the problem gave you. You may have used a nice, easier one. In that case, you're going to want to change your formalism or scale the results to match what the real problem's basis was. For example, I may not want to deal with a problem where I have 635 kilograms of reactant. I may just want to make that 100 kilograms to make my life easier. If you did that, make sure you scale back to the real problem. So a lot of this is really easy to say, much harder to do. So we're going to work 2 quick example problems. So the first, let's go ahead and say I've got 2 solutions. Both of them are essentially of gasoline. One is going to be octane rich, so it's 94% by weight octane, with the remaining percent being N-heptane, so isooctane and N-heptane. It's worth noting that octane rating is what we rate our gas by. And our second solution is much richer in heptane and much lower in octane. So this is a premium blend gasoline. This one will cause your engine some trouble. So let's say I want to try and stretch out my good gasoline with the bad stuff. So how much of solution 1 do I need to add to 10 kilograms of solution 2 in order to make an 87 octane solution? So this is regular gasoline, so it'd be 87% octane. So first thing we should do, diagram the problem. So using this, we're going to go ahead and arrange the problem in the total mass and percent component basis. And we already have a basis chosen for us, and that's 10 kilograms of solution 2. So this is actually kind of a tricky problem if you try and just solve it as a word problem as we would in most chem classes. But it becomes a little bit easier when I diagram it out. So I've got a mixing chamber, which I'm going to be adding in a certain amount of solution 1 to my 10 kilograms of solution 2 to end up producing my product. And I know the weight percents of each of these cases. So what I'm going to do here is do a classic strategy in industrial chemistry, and I'm going to set up one mass balance just for the total system, because I know the total coming in has to equal the total coming out. So 10 kilograms plus M1 has to equal M2. Or in another way of phrasing it, my M2 has to be 10 kilograms heavier than M1. Then the next strategy that's often easy to use is I can balance, add an extra balance for the components. So if I have 3 or 4 components, you may need several of these component balances to add up. So I'm going to end up balancing running a balance for my octane. So I know that I have in this solution It's 94% octane, but I have 10 kilograms overall. So using that, I know how many kilograms of octane is in solution one. I don't know how many is in my solution one, but I know that 80% of it is going to be octane. And similarly, I don't know what my total amount is, but I know 87% of it is octane. Now, one of the things you may note at this point is I have two unknowns, M1 and M2. Congratulations, I also now have two equations. So after this, it's two equations, two unknowns. So then you have to figure out who are you going to substitute into whom. So my personal suggestion is going to end up substituting in M2 into this equation because I already have M2 solved for the top equation. So then I can simply plug that in. The left side does not change. I just went ahead and dropped some units for convenience. And so I have 0.94 kilograms of octane plus 0.8 times M1. And then, well, my right side gets a little bit messier, but I can factor it out. Again, notice that inside the parentheses is just my equation from one, where we get a 8.7 kilograms plus 0.87 of whatever M1 was. So now we have our big equation down to a single variable. We rearrange it and isolate M1 onto one side, and we end up with a nice convenient system. 0.7 kilograms equals 0.7 times M1. Little division, we find out that M1, so my first solution, I'm going to need 10 kilograms of that to add to my octane rich solution. So congratulations, there we go. We end up being able to solve for M1, which is going to be 10 kilograms, and M2, which is 20. And this should hopefully make sense because it turns out this one we could have solved by inspection because my end product has a concentration that's literally halfway in between my two starting materials. So an even combination of both of the starting materials will give me my product species. However, it turns out that not all problems are quite so simple, and even without a reaction balance, they can get really messy as word problems. So let's look at another kind of similar idea. So let's say I've got a chemical mixture that I'm pumped that is 50% by mass benzene and toluene. So even mixture of benzene and toluene, fairly hard to separate. And I'm pumping through 1,000 kilograms per hour of this mixture. So I want to separate it by distillation into two fractions. So I'm going to generate a top stream, which is going to be richer in benzene, containing 450 kilograms, and a bottom stream that's going to be richer in toluene at 475 kilograms per hour. Now, what I want to figure out is what are the remaining benzene and toluene flows in both of these output streams. So one of the things to watch out for in this case is I'm using a mixed basis. I've got total plus percentages on my inputs, but I've got component masses on my outputs. And we can see this when we actually graph out, when we construct a diagram for the system. So one of the things should watch out for is that we have this mixed basis. Again, watch out. This should be 100 kilograms, 1,000, not 100 kilograms. And then again, components on the left. But one of the nice parts is once we diagram this out is we quickly are able to identify our unknowns. And that's the amount of toluene in our top stream and the amount of benzene in our bottom. So this is actually a fairly tricky problem, but fairly nice numbers that we're working with, because what we can do is quickly decide upon a nice basis. And it turns out that working with mass plus percentage ain't a great look for this problem. So I can rephrase the left side to say, wait a minute, I've got 500 kilograms per hour of benzene and 500 kilograms per hour of toluene. And then this lets me completely ignore my total balance, which I used last time, and I'm left with two component balances. So let's start by looking at the benzene. So I know I've got 500 kilograms per hour of benzene coming in, and I should have 500 kilograms per hour leaving. 450 of that in the uh, top stream, and an arbitrary amount in the bottom. So by quick inspection, we should be able to identify that the second component should be about 50 kilograms per hour. And similarly, for the toluene, 500 entering, 475 leaving the bottom. Uh, so that would leave 25 leaving in the top. So put it all together, we're able to quickly identify the input and all the components of the input and output streams. So again, one of the things to watch out for, the original phrasing of the problem looked very scary, but simply by diagramming out the problem and then splitting it into parts, we can often quickly solve what would otherwise look like quite complex problems. However, we have a couple of pesky issues to watch out for, such as the fact that we're not usually balancing just one unit operation. So next time we'll be talking about how we can combine together multiple unit operations. Till then, take care.